Hey everybody, it's Michael McClellan here. Hope you're doing well. It's 12 o'clock and thank you all for calling in. We're going to get started here momentarily. There's a couple things I would like to cover before I introduce Mike, and that is you guys have noticed, I'm sure, we've moved to the GoToWebinar platform, which means that you guys unfortunately can't talk. But we also don't have any problem with phones being muted and dogs barking in the background and that kind of thing. The way we interact is there's a chat box and there's a question box on the right of your screen. If you're an attendee, you should see some tools on the right of your screen, like a question mark. And feel free to go ahead and test that if you'd like to type in test to make sure we can see your questions. So please ask questions. Depending on the type of question, we will stop the presentation and answer it, or we may wait until the end to answer the question. So feel free to use the question box or the chat box. There's also going to be a poll or two during this webinar where you can answer yes, no, or one of the other answers. And that allows us to collect some information and to respond to you and plan future webinars accordingly. So that's all I have. And here is Mike Remlocken, who is a lead technical sales specialist with GE Multilin, who now calls themselves GE Grid Solutions.
Good morning, everybody. Well, I guess it's good afternoon now. I hope everybody's doing good considering the circumstances that we're under, and everybody's safe and keeping safe. So today's webinar discussion is going to be on arc flash hazard protection. Just a brief background on myself. As Mike mentioned, I'm the lead technical sales specialist at GE Grid Solutions. My area is application support for any questions concerning automation and protection. So anything with relays, automation, communication, SCADA, application support. My background is former utility protect PNC engineer with Con Ed in New York City, and I reside currently right outside Orlando, Florida. Okay, let's get started. So what is arc flash protection? So today's agenda is going to be basically an introduction into arc flash. So this presentation is for raising awareness about arc flash and how we deal with it. I'm going to talk about the arc flash phenomenon, kind of the definition, properties, and some of the impacts, specifically safety impacts. Briefly, I'll cover some of the standards, OSHA, NEC, some of the hazard assessment methods, mitigation techniques for arc flash, so that we understand what's out there for the technology, the existing technology, to be able to mitigate arc flashes. I'll try not to make this too much of a sales shift, but we will mention some. I cannot mention some of the technologies without mentioning some of the devices that we have. So I will mention some arc flash relays that are specific to GE. And the vastness of the topic does not allow us to cover all aspects. So there's going to be some polls that Mike are going to put out there. So if you can help us and answer that poll so we can better tailor these webinars in the future, so a certain topic that you might expecting to hear today and might not be there, please put that in there and we can expand on that in future seminars. I'll walk through some of the applications with arc flash relays. We'll learn how arc flash relays can be applied and some of the tactics that can significantly improve safety and enhance reliability of the system. And we'll concentrate more on low impedance differential protection for arc flash mitigation. I'll explain later what that is, and then we'll do some takeaways and some conclusions. So let's address what is
So
arc flash.
there's currently a poll open, and I would love it if you guys could just take a minute and answer that poll. And it'll only stay open for another 10 seconds, maybe 20 seconds. And then once you answer the poll, we will move on. And just trying to get a feel for when we should have these webinars.
Okay, so the NFPA and OSHA associations have their definition of arc flash, which is more for hazard and safety protection, obviously, or perspective. But what we're going to talk about this definition here is more of technical terms of what is arc flash. So arc flash is the flashover of current through air or vapor of the arc terminal material from one live conductor to another or to ground. The current passes through a vaporized arc flash material and ionized air. The resulting, okay, what happened there? The resulting hazards that it creates are intense light in the IR and UV spectrums, extreme temperatures up to 35,000 degrees Fahrenheit, which can cause obviously metals to melt, to bend, to deteriorate, which then can cause toxic vapors to be let out from these vaporizing material, such as copper. And because of the expansion of these materials, causes sound waves and pressure waves, which can then cause shrapnel to be thrown about at high speed, which can be very hazardous for personnel. Arc flash, how serious it is, just so that you know, at the bottom there, you can see 80% of the fatalities for arc flash are from burns versus electrical shock. So arc flash is not specifically electrocution, although it deals with, what it deals with really is heat and pressure. It's one of the most deadliest electrical parts of an arc flash incident. Arc flashes can be preventable, but on average, this is a number of studies that we've looked at, and on average, there's about 30,000 arc flash incidents per year, about 5 to 10 of these incidents per day in the US, about 400 fatalities per year, 7,000 burns, 2,000 hospitalizations per year. And we think these are basically on the low end of these numbers, because a lot of times when you get a hospitalization for a burn, it's not all the time recorded as where the source of the burn came from. So these are basically what have been reported. So we think these are very on the lower side, so this could be very higher. Arc flash has some interesting properties. So the temperature core of an arc can reach up to 20,000 degrees C or 35,000 degrees F in about 1 millisecond. Very, very short period of time. And just for some perspective, the surface of the sun's temperature is 5,000 degrees C. So it's basically on the low end, it's about 4 times hotter than the sun. And it can be higher than that depending on the arc flash energy. Projectile created by arc flash can fly at about 1,000 kilometers per hour. So very, very high speed, so it can cause a lot of damage. The pressure waves can be very, very high. The toxins emitted from vaporizing conductors can be very, very high and toxic. And the sun level can be above the threshold for pain. So it can cause nerve damage, hearing damage, and such. Somebody says they can't hear the presenter on the question. Can they hear? Did you see that, Mike? Hello?
Yes, I'm working on it.
Okay, but you can hear me though, right?
Yes, I can hear
Obviously.
you, and I can hear you through the computer as well.
Okay. So arc flash can oscillate and escalate if not constrained in a very, very short period of time. We're talking about milliseconds here. As I mentioned, the 1 milliseconds to get it to its hottest point. And because of that, a single phase fault can engulf and evolve over conductors, evolving to a 3-phase fault for lingering arc flash cases. The first step to assess the hazard level is to estimate the actual energy created by the arc flash, called the incident energy. Why? Because of the amount of energy releases defines the intensity of the arc flash. Right? Let's take a look at this formula, one of the formulas that we use for determining arc flash energy released. And you can see that it's directly proportional to the short circuit current, the voltage level, and the distance between the arc and where you're measuring it from. So it would be from the arc and the personnel. So the farther you can see, the farther you are away from the arc flash, the less incident energy we'll see by the distance squared. So some of the incident energy varies by obviously the larger short circuit current, the higher energy, the higher the voltage, the operating voltage, higher the energy. The system grounding is very important too. So if the energy does not have a good path to ground, that can create more energy for the arc flash too, or lingering energy. And the characteristics will vary by environmental, the type of energy that it dissipates, the conductor spacing, insulation, the distance that you are away from the arc flash, the enclosure, and obviously the interrupting characteristics of your relay and your breaker. We'll go through a lot of these as we go through the presentation. So there are many causes for arc flashes, but most of the typical ones are listed here. Accidental dropping of tools or broken parts can cause multi short circuits and initiate arcs. Aging components, corrosion, and impurities result in the insulation deterioration and in time the release of arc flash through that deterioration. Poor quality work, such as loose connections, damaged insulation, that can severely compromise the connection quality and cause arc flash incidents. Corrosion over time weakens the contact between conductor materials, terminals, increasing resistance through the contamination and results in heat generation and sparks, which can lead to obviously arc flash events. Pollution, also pollution in insulating surfaces provides a path for current. Fumes and chemical vapors in the air can cause, so depending on your environmental condition, that plays a big part of the incident, arc flash incident energy, as well as the arc flash, number of arc flash incidents. Improper design and improper equipment selection can also increase arc flash incident energy, such as if you have a slow breaker, you don't have a fast breaker, obviously the slower the breaker takes to operate to clear the fault, the longer the arc flash energy is sustainable. And obviously, if you haven't sized your conductors properly, size your buses properly, that can lead to more insulation breakdown over time. Arc flash can be caused also by animals, so a poor rat or snake crawling into a switchgear, trying to escape from, I guess, from the north from the cold, and from the south here from the heat. So a lot of causes of arc flash events out there. These, just name a few. Now, what is the damage mechanism and how does it develop? As I mentioned, it develops very, very quickly over time. The optical emission happens right after the onsets of the arc flash. So in this slide here at about 0 millisecond, that's where the arc flash starts, and then about 5 millisecond, basically that's when the optical emission peaks, and it continues to pulsate to generate all of the energy for the arc flash incident energy. And then about 10 millisecond, that's when the pressure wave reaches the maximum, and then it starts to disappear after that. The heat emission about 100 milliseconds starts to develop heat which can melt cables, seals, insulation. About 150 to 200 millisecond, that's when it's going to start, the heat is going to develop to start to melt metals such as copper and steel, and which can cause vapors released by these metal toxic vapors. So what are some of the mitigation techniques? We're not going to be talking about avoidance techniques, but more moderation techniques. How do we moderate it? The fact is, we probably cannot eliminate the hazard. There's very, very little we can do to completely eliminate the hazard. So what we have to do is basically mitigate the hazard. So some of the enhanced reliability designs we can build into our system for controls, engineering controls, design of the equipment and such, are providing mechanical design, the proper robust mechanical design, sizing of all the equipment, proper interlocks to minimize human errors. And we'll talk a little bit more about that later. To redirect incident energy, we'll talk about how we do that with arc resistant switchgear. Short circuit rated equipment, be able to interrupt and clear the fault in a specific amount of time. Maintain our voltage, because obviously voltage stability can cause insulation breakdown over time and deterioration over time. Proper grounding and harmonics mitigation, fast and reliable protection. And a lot of the concentration we're going to talk about later is basically how do we have arc flash mitigation using fast and reliable protection systems. But just looking at this upside down triangle here, as I mentioned, we really cannot eliminate the hazards. So the best we can do is provide some sort of engineering controls to reduce the risk or substitute less hazardous elements. And the other techniques, where proper PPE, have proper interlocking admin controls and signs, warning signs to tell personnel when they are working in front of an arc flash zone to be able to, so that they take the proper mitigation techniques such as wearing PPE or even staying away from the arc flash zone. The term arc flash has very much crept into electrical jargon in the last few years, because previously we didn't get much taught to arc flash. We designed our equipment best we could. But because of the safety issues associated with arc flash, it has become a very critical part of our assessment and prevention measures. And a lot of times we will spend a lot of money to be able to, sort of time and money in design to be able to mitigate arc flash incident energy so that we can reduce the risk and hazard for personnel. There are standards out there, OSHA, NFPA, IEEE, NEC standards that basically talk about, what some of the things you need to do to be able to provide these mitigation techniques. And one of the basic things is you need to know what kind of arc flash incident energy you have. So you need to do an arc flash analysis to be able to determine, what is your arc flash energy, because you don't know what type of signage to put, you don't know what type of boundaries to create, you don't know what type of PPE to wear unless you actually know what is the arc flash energy that you're going to be exposed to. So some of the categories for PPE, depending on the energy level. So once you've done your analysis and you determine what your energy level is, Then you're going to place these signages for personnel to be able to then, once they get next to an arc flash hazardous zone, so that they know what type of protection that they need to wear. And you could see for very little increase in arc flash energy from a category 2 to category 3, we're talking about going from something from face shield, helmet, FR overalls, gloves, to something that resembles almost a spacesuit, multiple layers. And it could be quite the production if you need to get into one of these arc flash resistive PPE equipment. And so time, cost, downtime, and such can play a big part of that, besides obviously the risk to personnel. So a lot of what we do today is to use power system softwares like ETAB or Easy Power to provide system arc flash calculations based on the various standards. This is an example here. We define and calculate zones using the IEEE method for low voltage switchgear. This is, I think, from Easy Power software. I can't remember exactly. I think it's Easy Power. Regardless, let's take a look maybe at feeder F3 in this case, and you can see based on the study, it's a 23K short circuit, three-phase voltage fault with about a 50 millisecond arcing time, which is about the 2.7 arc flash incident energy per centimeter squared. And you're talking about going to category 1. So this is basically a pretty much your first level. So this is going to be level 1, and then you could see for F2 and F3, it's about 10. So that we're talking about going to category level number 3. So that will require quite a lot more PPE to be able to go into those arc flash zones and work in those arc flash zones. So one of the strategy number 1, mitigation strategy number 1, is to be able to shield personnel from the zone, from the arc flash zone, right? So NFPA defines PPE characteristics and categories, and I mentioned what those are, and I put them back here. You could see, arc flash energy 4, with PPA number 1, so limited approach boundary, so you expect maybe to get some shock. Arc flash energy level 2, limited approach boundary, you could get some shock, maybe some vibration, maybe even flying shrapnel, depending. Prohibited approach, so it's kind of like going into a spacesuit, and then we have a zero distance, where it's basically you just don't want personnel going to that zone, even with proper PT, unless it's absolutely necessary. So we want to be able to shield personnel from getting into the zone, and if they do need to get into the zone, to be able to take the proper precautions when they do. The strategy number 2, mitigation strategy number 2, we want to minimize event equipment damage. So when something does happen, we want to be able to minimize the extent of the arc flash incident. One of the ways we do that is with arc resistance switchgear. There's various standards for these arc resistance switchgear. There's various, for example, the ANSI IEEE, there's various types. So these technologies to minimize equipment damage are the most effective strategies, but the pros are they can be very costly. The arc resistant switchgear has been around for a while. What it does, it redirects arc energy out of the equipment through ducts or vents away from the operators. And you can see in this picture here, see that duct or vent on the top, which goes to a location where personnel would not be in that vicinity. All primary compartments are provided with pressure relief flaps located in the top side of the switchgear. So any overpressure inside a compartment by an internal arc is released through these pressure relief flaps. There are some IC and ANSI standards defining the required type tests to be able to say you're ANSI type 1 or, for example, ANSI type 2C. An example with type 1 switchgear, an operator can approach the front of the switchgear lineup and won't be any exposure to any type of arc flash or arc blast. There are also some extinguishing techniques to be able to deal with arc flash once it occurs. So the concept is based on detection and removal of an arcing fault before it escalates into an arc blast or elevated arc hazard risks, such as high temperatures, which as I mentioned, is the most severe. So basically, with the Type 2C, you have arc flash resistance from all corners of the switchgear, so from the front, back, sides, and between the compartments. And then for type 1, you would only have it in the front so that you can only approach from the front of the switchgear. The cons of this is actually, as I mentioned, is very costly than just buying a standard breaker and switchgear and associated switchgear. It can only do it for new installations, probably very, if not impossible, to upgrade an existing switchgear to be arc resistant. But as I mentioned, it's one of the most effective techniques for mitigating arc flash and mitigating the arc flash incident energy, and hence to be able to make it safe for personnel to work in and around the switchgear. Mitigation strategy 3, deploy preventive maintenance tactics. One of the more effective is to reduce the access to the high-risk areas. So interlocking systems can be set for mechanical parts to prevent improper operation. For example, a circuit breaker can be closed only when it's between the connected, cannot be closed, sorry, when it's between the connected and test disconnect position. Some switchgear, drought switchgear is equipped with interlocking systems. Most today in today's market should be equipped with these interlocking systems. The energy reducing maintenance switch is a very simple but effective solution that's described in a lot of the standards as one of the techniques that are approved for arc flash mitigation. So what it basically does is it decreases the fault clearing time, and thus the incident energy is reduced greatly during this, what we refer to as maintenance mode. In the picture on the right, the relay trips without intentional delay when the maintenance switch is enabled and an incident occurs or a fault occurs. So what you would do, you have some sort of switch, push button, SCADA control to bypass any coordination that this main breaker needs to do when any of the downstream breaker, and it will go into strict instantaneous mode, instantaneous overcurrent mode. So whenever there's a short circuit or arc flash, it will trip the main breaker right away. The disadvantage is using this, it's not in service all the time, only when the maintenance switch is in the maintenance position. And obviously you need controls for that. So if you want to make sure that switch is on when personnel is in the area, so you need to have some control for that, engineering controls for that. When it is in the maintenance position, the con is for faults external to the downstream breakers. So a fault downstream of the breaker will cause the main breaker to trip. So you risk the over tripping for an incident to your main breaker. And if you don't have any sort of backup, then obviously for a fault downstream in one single feeder, you could take out multiple pieces of switchgear and maybe have a blackout in your plant or facility. But very easy to maintain. Most electric microprocessor relays on the market, very easy to do this. either you can add a maintenance switch or a push button of some sort. You can see one's mounted on this panel over here. You could use a push button in the relay. You could do it from, if you have communications to the relay, you could do it from SCADA, so you could put it in maintenance mode before you even go out there to do work. And the effect is basically you're bypassing all of these coordination curves and you're tripping very, very close to the arc flash incident energy, where you're going to reduce that time significantly.
Mike, we have a question.
Okay, go ahead. Sorry.
And it's a good question. It's from Mike Fedini. Does the arc resistant type of switchgear reduce the PPE requirements?
Yes, obviously, yeah, it does. I'm not sure. Obviously, it is when the switchgear is enclosed and it's in normal position. Obviously, all games are off. If you need to do some sort of maintenance, you need to open that piece of switchgear up, because then it, bypasses those controls. But yeah, strictly when the switchgear is in normal operation, depending on the arc flash energy, it can significantly reduce it. And by reducing the arc flash energy, it can significantly reduce the PPE required to be in front of that switchgear. Obviously, if you're going to open up the switchgear, that goes out the window. But if you're going to open up the switchgear, you're probably going to de-energize it. You're not going to be working a live piece of switchgear.
Mike, a follow-up question to that is, if it does contain it, what happens to the switchgear? Could it blow up still and you have to replace the gear, or it just prevents safety, or what? The personnel.
So yeah, that's a good question. Obviously, if it's designed properly for the incident energy, that if it's the incident energy is what it's defined for, it should not cause any damage or anything to the equipment itself, because a lot of that pressure should be vented properly. But obviously, it all depends if it's designed properly. That's very important. That's why it's very difficult to sometimes size these arc flash, and even cost prohibitive. If you have a lot of arc flash incident energy, it might be cost prohibitive for somebody to build you something that will be able to, vent all of that pressure safely. Thanks for that question. Very good. So another technique is
another question, Mike. That's a follow-up is, can this be installed in MCCs? And I'm not sure what this is referring to. Is perhaps it's protective relays?
Which technique? So I'm assuming it's maybe the maintenance switch. Yeah, the maintenance switch can be in any type of device, but with an MCC, it's only going to affect that MCC. So really, where you want to put this maintenance switch is the main breaker feeding into that MCC, right? Well, it depends. Where is the arc flash you're trying to protect against? Is it at the motor? Is it at the MCC? Is it in the switchgear? So the answer is you want to protect for every single incident energy. So where it's most effective to put the maintenance switch is the main incoming breaker. But as I said, it's going to be if you have an incident while it's in maintenance mode, you could over trip, and cause issues or blackouts in the plant. So hope that answers the question. I'm not sure if that I understood it correctly. Modern protective relays, microprocessor-based relays, have extensive communication control capabilities that can be used for remote operation, like closing and opening the switching devices. So, to be exposed to arc flash energy, you have to be in front of the equipment or the vicinity of the equipment where the arc flash energy exposure is. So you want to stay out of that. So area, that's the most mitigating, factor. Is if you stay out of that area, you're not going to be exposed to the hazard. So controlling and operating breakers remotely is a very effective way of doing this. I was in a facility about a year or two ago, and we were upgrading all of the relays to have this capability. But while we were doing the upgrade, as we were taking pieces of equipment out of service to do the upgrade, basically what the guy would do to open the breaker, he would just run down the aisle and grab one of the switches and the trip switch, and as he's running, touch the trip switch so it trips the breaker and continue running. So that's a technique too. Obviously, with modern microprocessor relays, if you have communication, serial or Ethernet, if you saw the webinar last week, we talked a lot about what the advantages of Ethernet is over serial. You can basically operate the equipment remotely and not have to be in front of it to be exposed to the hazard. And obviously, once it's de-energized, then you can then have carte blanche to go and work on the piece of equipment. Remote racking devices. This is also part of options in certain switch gears, especially low voltage switch gear these days, because you might not have remote communication to every piece of your low voltage switch gear. So you can have these remote racking devices. You can see this guy has some like a little lead that he plugs into the control, and then he stays far away to be able to operate it. So the pros, obviously, limit exposure. It can be inexpensive way of doing it, depending. If you need to add communications, then it's going to be a little expensive to add it. But the cost adder of adding some of these remote racking devices, I'm not sure exactly, but I assume I would think it's not that much to be able to add these type of remote racking controls. Obviously, the cons is obviously provide safety for personnel because the personnel is not in front of the equipment, but we still have the arc flash hazard is still there. So it does not mitigate the equipment damage. It might not be available for every circuit breaker. So like as I said, the remote racking unit might not be available for an existing switchgear because it was never designed as part of that switchgear. So you'd have to speak to your switchgear manufacturer, find out if that mechanism is available and if it's retrofittable to particular. So there might be third-party ones out there too. I know there's some third-party ones that you can add to certain switchgear. So I'm not 100% familiar with them though. They can be cumbersome because you got to walk around with that, lead and that switch, and then you got to plug it in to be able to. So sometimes it's removable. So the act of just plugging in, right? You're still in front of the switchgear. It might be very limited time, but you're still in front of the switchgear, so you're still exposed a little bit to the hazard, but the probability of the hazard happening while you're plugging that in is very low, because the probability is during switching, the probability increases during switching. So once you're away from the device while you're switching it, then you reduce the risk. Reduce the exposure to these incidents. Obviously, always work on de-energizing equipment if possible. Make sure your insulation conductors are sized properly, spaced properly. So mechanical designs, have IR scanning windows so you can take a look to make sure you don't have any arcing going on there before you do any switching or start to work on a piece of equipment. Hinge versus bolted doors, obviously arc resistant switchgear I talked about earlier. So a number of ways to reduce your exposure here. And finally, strategy number 6, which is what we'll be concentrating on more, is the I see John posted a link here on some remote racking SU mechanism for certain switchgear. So you guys can click on that link if you need some more information on that. Select the appropriate system grounding. Obviously, you want the energy to be able to go to ground and dissipate as quickly as possible. Reduced the short circuit or breaking current. One of the most effective technique is energy is directly proportional to fault current, as we saw in the previous equation. And it's also proportional to tripping and arcing time. So if we can reduce those, any one of those two, that will significantly reduce our released energy or incident energy. Grounding is a vast topic, so maybe we can send a poll out to see if you guys are interested in having a seminar just on grounding and system grounding. But it's very important, but it's not something we're going to be talking about today, but just know that that's also a mitigation technique, is to have proper system grounding. Many ways of reducing short circuit current, either by reducing the amount of short circuit or reducing the time of the short circuit current that's when it's going to be present on the system, such as like current limiting fuses, using reactors to reduce the short circuit current are some of the examples. For reducing the fault clearing time, install faster breakers, obviously. You can get 2 to 4 cycle breakers these days, maybe even 1 cycle breakers depending on the voltage level. Obviously, it also depends on cost. So all of these require some sort of cost adders to them. And finally, to reduce the incident energy or arc flash energy is to apply protection functions that are very fast, that can be fast, be able to trip the mechanism. So it's a combination of how fast the protection device is to sense the arc flash and how long the breaker takes to clear the arc flash or fault condition that caused the arc flash. So in addition to having faster breakers, we can install arc flash protection relays. They're not arc flash resistant relays, they're arc flash protection relays. The purpose is putting these devices in to reduce the fault clearing time, total fault clearing time. Do we have any questions there, Mike, that I haven't answered?
I
Please
don't
ask
think
questions.
so.
Please ask questions.
Is this a good time for the poll?
Oh, yes. So we're going to talk about the protection techniques for arc fact detection and mitigation. We're going to talk about, specifically, we're going to talk about one of the most effective ones is differential, specifically bus differential protection. So Mike's going to put a poll out there to see, what kind of bus protection that you guys use. One of them is going to be, we're going to talk about, is blocking. One of them is going to be whether it's just, there's no really bus protection, you depend on coordination. One of them is high impedance bus protection. The other one is going to be low impedance a bus protection. The other one is going to be just having like a unrestrained or overcurrent bus protection. So we're going to, and that poll is out there, so please answer that if you can. So some of the arc flash detection techniques we're going to talk about is zone interlocking with relays, bus and differential protection. Our concentration is going to be on bus and differential protection. And also we're going to talk about using light sensors, because what we mentioned, arc flash energy, one of the first things that gets emitted is light. So we can use that, and that's the fastest thing that we can detect, is right? Nothing speedier than light, right? So it can offer us fast detection of arc flash. Before we talk about the zone interlocking, one of the techniques that I'm not going to talk about, which is on the pole, is the overcurrent or unrestrained differential. So basically what it is, it's just a bunch of CTs parallel together, like in this case, all the CTs from the main and all the CTs from the breaker, parallel together and going to an overcurrent relay. And going into an overcurrent relay. The very good way of doing it, provides fast protection, but it also very unsecure, meaning CT saturation, it's very susceptible to inaccuracy in CTs, it's very susceptible to. So in order to deal with a lot of these so-called issues with overcurrent protection, overcurrent bus protection, we generally increase the sensitivity and we add some time delay to overcome some of those. If if you have an external fault and your CT starts to saturate, you want to give the CT enough time to recover. Or if you have a fault with a lot of harmonics on it initially, you can cause different mismatch in the CTs during that when you strike the fault. So you want to give that overcurrent some time so that it settles down so it doesn't misoperate. And so it kind of defeats the purpose a bit. If I have to add some sort of timing delay, then I'm increasing the arc flash energy. And two, if I need to increase the sensitivity, then I might not be capturing all arc flash incident events. So a better technique is the zone selective interlocking. And it's very fast. It could trip in up to in less than 5 cycles, depending on the design. And what it does, this particular one here, I'm talking about uses IC61 and 50 goose messages, which is a way to communicate peer-to-peer from relay to relay. So what it does is, if there's a downstream fault, the relay on that feeder, for example, feeder 3, if it senses a downstream fault, it will send a blocking signal back to the main relay, tell them, hey, the fault's in my zone, it's not on the bus, you don't need to trip. If the main relay does not receive a blocking signal from any of the downstream devices, then it knows the fault's on the bus, and then it's going to trip. Very easy to implement. All relays today have some sort of a communication port which supports ICC1 if they use messages. At least ours do, all of ours do. Easy to implement, just adding some sort of switch. You can have 2 switches if you want a redundancy. All our relays have up to 2 ports on them. The other way of doing this is to hardwire those blocking signals from the relay back to the main relay. Obviously, the disadvantage of doing that's a lot of wiring required, a lot of cables that you got to run. And the other thing is maintainability of that system. If there's a problem with the system, troubleshooting it. If there's a problem with it, you might not even know about it until there's an event and then it fails to operate. With the communication medium using Goose, it's constantly monitored, so any disruption or break in the communications, you know about it right away. And the wiring is very limited. Low impedance bus differential. So we'll talk a bit about low impedance bus differential, but before we do, just want to mention some of the other bus techniques out there. I mentioned the unrestrained differential, which is basically the overcurrent one in the pole. I mentioned the zone interlocking or blocking scheme. There is also high impedance bus differential. We just don't have enough time to talk about all of them today. So I'll just leave it at the high impedance is basically, again, just like the overcurrent, but more secure where the CTs are all parallel together. But it's a more secure method, and it involves basically paralleling the CTs. If there's an external fault, the current circulates in the external circuit. It doesn't go into the circuit of the relay. There's an external fault that goes in the circuit of the relay. It can be very sensitive, so it can be, unlike the overcurrent, it's very sensitive. And as I said, unlike the overcurrent, it's very secure. And it's been a proven technique we've used for a long time before the we started using low impedance percent differential. The cons of using it is you need dedicated CTs because all these CTs have to be rated the same. The CT ratios have to be the same. And thirdly, if there's a problem in the circuit, you might not know about it until it's too late because you're not monitoring the individual CTs, you're just monitoring the parallel combination of several to 10 sets of CTs. So it's difficult to be able to troubleshoot it when there's a problem. It's very difficult to tell there's a problem. So the low impedance percent differential, so most applications today, if you're building a greenfield project, probably the type of protection you'd select is the low impedance bus differential. But before we get right into how we do low impedance bus differential, just want to mention, challenges to protecting a bus zone. Obviously, we have high fault current levels, which cause we talked about high incident energy, high arc flash energy, which can cause all of the mechanical issues and personnel issues, safety issues. But it also CT saturation issues that we have to deal with when we're talking about differential protection. Let's just keep going back. Bus topology, if how many breakers do you have on the bus? You could have up to from 4 to up to 20 something breakers, depending on the type of bus. So we need to be able to address all of those. And dynamic topologies, meaning reconfiguration of buses. So you might have one day generator 1 might be in bus 1, and tomorrow you might switch it over to bus number 2. So be able to deal with those dynamic topologies of buses. And security of bus protection is very important. You do not want to misoperate on a bus because it affects multiple loads, right? So if I trip a bus out, I'm going to cause loss of customer load, which could lead to damage in customers' assets, detrimental impact on industrial processes. I have downtime in multiple processes, and stability issues because of the amount of short circuit current that I'm going to draw for that bus fault can cause stability issues. So what are the advantages of having high-speed bus protection? Obviously, for arc flash energy is reducing the trip time to most relays today are less than a cycle or a cycle for bus differential. So it can reduce any type of arc flash incident to about level 2, if not level 1, at least, because we're talking about, depending on the breaker that you have, we're talking about no more than a cycle for the relay, maybe 4 cycle for the breaker, could be 5 cycle, or if you have a 2 cycle breaker, then it could be 3 cycles. So it's very fast, and you can reduce your rating to either level 1 or level 2 very easily. It has no impact on system coordination, so bus differential operates with no impact on system coordination. It does not have to coordinate with anything. It's just going to operate for faults on the bus. It also operates without operational intervention, unlike the maintenance switch. Remember, the maintenance switch needs to go into maintenance mode when you're working there. With the bus differential is always there, and it's always going to operate. And because of the fast operation, it minimizes damage to the equipment. So that means shorter repair time, so longer downtime for your process. So it gives a lot of advantages of using low impedance bus differential. But what it works is basically Kirchhoff's current law. So current in to a node should equal current out of a node. So that's what it does. All the CTs are connected directly into the relay, unlike the high impedance where they're parallel. So you can monitor the CTs individually. So if you have a problem with the system, you can tell if there's a problem one of the CT. It has built into the algorithm techniques to mitigate the effects of CT saturation. So it's very secure and very fast. So as I mentioned, it's a current in equals current out principle. So if the current out is not equal to the current into the bus, then we know that there's a fault internally and we can trip. However, we have a percent characteristic, which we call a restraining signal that we get. So this is a diagram of what it looks like. So we have a fault that starts from time t0, and then we have an external fault. You expect the trajectory to go from t0 to about t1, so with no CT saturation. If there's CT saturation, what's going to happen initially is going to go to t1, and then as the CT saturates, and it's going to go to t2, and then it's going to go into the tripping region. So what we do to mitigate this, you can see these lines here, these are slope settings in the relay. So we can increase these slope settings to be able to mitigate the effects of CT saturation, so that we could deal with external faults with CT saturation, still be able to trip reliably and not misoperate for an external fault. However, there's only so much limit to these curves that you can do. So sometimes if you have some extreme cases of CT saturation, we have another technique within all our relays, what we call a directional principle. Basically, what we'd say is we have a high differential and a low differential. We split the curve into two. And we say, hey, in region number 2, we have large currents, so CT saturation is easy to detect. The security required, we only require CT security if there's a saturation detected, whereas in the region 1 of the curve, saturation is very difficult to detect because the fault currents are lower. And due to DC offset, we could have saturation due to DC offset, which can be very low. So more security is required in that region of the curve. So what we basically do is we have a directional, so say, hey, before the CT saturates, the CT does not saturate right away. There's a finite time before the CT saturates. So we can determine before the CT saturates the directions of all of these currents. So obviously, if the fault's on the bus, they should all be within plus or minus 90 degrees of each other. If there's an external fault, like I'm showing here, then at least one of them will be about 180 degrees out from the others. So during the region 1, I basically always look at the directional flag because it's it's harder to detect CT saturation there, so I want more security. So the directional flag gives me security. But if I have a high level fault, if it's internal, meaning there's no CT saturation or limit, where it basically goes from right, it does not go to T0 anymore, it goes right from T1 to T2. So I know that that's an internal fault with so I don't need to look at that directional flag. However, if there is an external fault with CT saturation, I see that it goes from T0 to T1 to T2, then I say, hey, saturation is detected, then I need to look additionally at the directional flag. So I still have fast tripping, but I have security for external faults. Some of the application with light sensors, we're getting pretty close to the end of the presentation here, the 1 hour. So I'm a little bit behind, but basically what the light sensor is, obviously it detects light within the switchgear caused by the arc flash. Very fast, right? It's arc light is very fast, so we can detect light very fast and like a couple of in less than a milliseconds. Combined light and current yields faster and more secure response. So meaning that we don't want to just look at the light because there could be other incident that could cause light, like somebody working on a dark switchgear and a flash, lightning flash. We don't want just to go off light because it's not the most secure, because we could have other sources of light. So what we do is we go with light and current, but this is a different current detection that we have in our relays than your normal overcurrent. These are very fast overcurrent. We talk about fast is about less than 3 millisecond pickup. So that combined with the light sensor, we get both. Then we're going to say there's an arc flash event. And we're talking about operation time of that plus contact operation time. We're talking about can be less than 5 milliseconds. So very, very fast. We have different types of sensors. Most of our relays have up to 3 to 4 arc flash sensors, light sensors. So we have the point sensors, which can go up to about 18 feet. They could be used for anything, for switchgear, motor, transformers, generators. Then we have another 350 relay, which is a similar, but it also includes loop sensors. So loop sensors, you could loop it into the switchgear, so you can cover multiple lineup with one sensor. The point sensors, with the point sensors, it can only cover where that point sensor is located, right? What we do is we have an adaptive light threshold. So basically, we're starting off at a certain light level, ambient light level. And as the ambient light level, we adjust to the ambient light level, we change that default level. So we're constantly adapting to the ambient light level, because we want an increase of light level that we're looking at, right? So if ambient light causes an increase, that can cause the sensor to misoperate. So we need to know what the ambient light level is. So we're constantly adapting. We need to also, check the sensor all the time to make sure it's operating properly. So what we do is we do send periodic short pulses of pulse on the transceiver, and we receive it back on the receiver, and we know that the sensor is working properly. This periodic health check does not affect the operation time of the sensor at all. Where do you put these sensors? We recommend, obviously you want to put them in the switchgear compartment, either the main chamber, the cable compartments, the low voltage compartments, and wherever arc flash incident energy is possible. Right? We do even though when the sensor operates, it takes light and current to be able to operate the output of the arc flash. However, if you need to specifically build your own logic around this, we also provide the light and the IOC as separate items, so you can create your own logic if you needed to. So depending on application specific, you can create your own logic because you have all of those points available. So applying the sensors, the loop sensor is mostly for the entire switchgear lineup, whereas point sensors for the specific switchgear compartments. Point sensor is always going to give you excellent sensitivity. Loop sensor not so much, because we're talking about looping that sensor wrong. So we're talking about fiber degradation, fiber signal degradation, and such. Reducing arc flash energy. So we're just looking at with using these arc flash units versus just the overcurrent, and you could see significantly in this example reducing it from arc flash level of 3 to 1. So you're talking about a significant reduction, and most of the time you're going to be able to reduce it to an arc flash level of 1, assuming you have a fast acting breaker or fast interrupting breaker. So we're talking about reducing our PP requirement or hazard, everything for personnel or safety, with using either the light sensor or the bus differential. So we talked about the challenges of arc flash. It happens, right? Very fast event with immense safety and damage effects. No single proactive solution that fits every situation. It's up to what do you want to spend. If it's a green field, brown field, it depends on the application. If you just want a quick fix, it impacts personnel, obviously, equipment damage, downtime, production loss, economic loss. Solutions we talked about, deploying those 6 mitigation techniques or solutions. We talked extensively about bus protection as being on the light sensor as being the 2 most effective, combined with a fast acting breaker. Advantages of, implementing arc flash protection, arc flash hazard protection is obviously number 1, worker safety, extended equipment life. You're subjecting equipment to less arc flash energy, so less stresses. A reduction in downtime. You probably will be able to reduce the damage caused by the arc flash and be able to repair it in a timely manner. You're not compromising, protection and coordination with an arc, like for example, with a low impedance differential relay. There's no coordination required. So You're not compromising anything there. So you could still trip for faults on the bus and not trip for faults external to the bus. And diagnostic ensured detection reliability. So depending on the technique, like relays, communication, you're constantly doing diagnostics of the system, and you can tell when something's wrong so that you can go out there and be able to maintain it. With that, Mike, do we have any questions, additional questions?
Yeah, there's a couple.
How do light sensing inputs affect the IE during active maintenance? Is something we can use, Laura? So the light sensor does reduce the arc flash levels. So you are reducing the trip time. So trip time equals arc flash energy, right? So you are reducing the arc flash energy using light sensor. It is intended for equipment protection as well as personnel protection. So it is intended to be able to, for maintenance personnel, to protect them. So one of the main reasons of using light sensors is actually probably is personnel protection, because you're not really gaining much more otherwise versus a low impedance bus differential. Can I borrow one of your arc flash hazard suits from an, okay, I'll leave that one for John.
I'll take that one.
All the questions? Did I get all the questions? That's all the ones I see in the chat there. Any other ones, Mike?
Yeah, these are great. Thanks so much for your attention, everyone.
Yep.
We did put a poll up there, so if you'll rate Mike on his presentation, if you can just give him a 1. If you thought he was, if you fell asleep more than once, please give Mike a 1. And if you thought Mike was great, then give him a 5.
All right, thanks everybody, and I guess we'll conclude and hopefully see you in the
Good job,
next.
Mike. Thanks.